Welcome back to Integral Calculus. In this video, we're going to be walking through a review of some of the concepts of trigonometry. Usually, a lesson on this title is going to go through things like the trigonometric ratios, special angles, those sorts of things, maybe basic trigonometric identities. Those are all things that I expect that you know inside and out at this point, given how much we've used trigonometry over the past semester and a half. Instead, I want to look at trigonometric functions, domains, ranges, and the properties of the inverse trigonometric functions. Let me get my head out of the way, and let's start off with the simple sine function. There we go. The graph of y equals sine of x looks something like this. The maximum value is y equals 1. The minimum value is y equals -1. And it repeats through this pattern over and over again. The most notable thing for us is that it is very much not a one-to-one function. So sine does not have an inverse. But we've used inverse sine before. It's a thing that comes up and is necessary in a lot of problem solving. The answer to that, the answer in a lot of places where an inverse doesn't seem to exist but we need it, is to create a branch cut. So I'm going to construct a new function. The notation here doesn't really matter. We're going to use it for about 30 seconds and then never again. But I'm going to call it sine bar. It's y equals sine x with a bar written over top of it. And it's the same thing as y equals sine of x, except that the domain is restricted to be from -pi/2 to +pi/2. The distance it takes to get to the minimum value and the maximum value. So you go through the entire range exactly once without ever doubling back. So that is a one-to-one function. That is a function which has an inverse. And the inverse function here has many names, but it's going to have a domain from -1 to 1 and a range from -pi/2 to pi/2. Right? The domain and range of a function and its inverse just switch. So the domain was from -pi/2 to pi/2. I said the range and just realized I never wrote it down. The range was from -1 to 1. So if I want to construct the inverse here, I'm just going to take those points and kind of flip them on their side. And I get this function. There are several names that this function goes by. We're going to call it the arc sine. Calling it the inverse sine, again, doesn't make sense because sine is not an invertible function. And avoiding the superscripts avoids all of the issues with trying to mix superscripts and primes and so on and so on. But again, just flipping the domain and range, the domain here is from -1 to 1, and the range here is from -π/2 to +π/2. And then we could do the same things with the other inverse trigonometric functions. Here I've got the graph of y equals cosine of x. We definitely want to include this part because that will give us the first quadrant, which is usually the most important. That part doesn't help because it would still fail the horizontal line test. So instead, here we have to continue on in that direction. So the domain of this function is going to go from 0 to pi, and the range is going to go from -1 to 1. We can get our arc cosine function, which will look something like that. The domain here will be from -1 to 1, and the range in this case will be from 0 to pi. And right away, I hope you see why I'm taking the time to go through all of this. The range of the inverse sine function and the inverse cosine function are basically completely different from each other. And that's a pattern that's going to continue through the other functions that I'm going to care about, and can be a problem. So it's always something to pay attention to. Make sure you know which function you're dealing with. Make sure you know the domain and range of that particular function, because it can come up and it can bite you. Of the functions we're going to be working with, I think that the secant function is the messiest, with all of its asymptotes, and of course the no man's land in here, where there is no output value between 0 and 1. Right, making our branch cut, again, this space here in the first quadrant is definitely going to be part of it, and then we're looking for the next nearest space, which almost always is taken to be this bit right here. So if we take our branch cut, y equals secant bar of x, the domain is going to be from 0 to pi/2, union with from pi/2 to pi. And then the range will be from -∞ to -1, union with from 1 to infinity. That is a mess, that is a nightmare, but it's what we have, so we deal with it. All right, but flipping that on its side, we get the arcsecant function. And again, just swap the domains and ranges. The domain here is from -infinity to -1, union with the interval from 1 to infinity. So the stuff between -1 and 1, again, is a no man's land. And then the range is going to go from 0 to pi over 2, not including pi over 2 as it jumps from pi over 2 the rest of the way to pi. And then finally, the tangent function, which I think is my favorite for dealing with in inverse functions. It is definitely the best behaved of all of the inverse functions. Choosing a branch cut, this central bit right here makes an incredibly obvious choice, in my opinion. So tangent bar, the domain here, again, it's going to be restricted because we are dealing with a branch cut. The domain is going to go from -pi over 2 to +pi over 2. That's definitely the smallest of all of the domains we deal with, but that's okay. It gives us everything we need. And because of the asymptotes on either end, the range here is all real numbers from -infinity to +infinity. But that gives us a really convenient way of graphing out arctangent. And again, the beauty of this, the domain of the arctangent function is all real numbers. Whenever we can use the arctangent function, it is our favorite inverse tangent function, or inverse trigonometric function. Even if the range is fairly small, going from -pi over 2 up to pi over 2. Now that we've gone through what most people consider to be the hardest part of trigonometry, now let's go to the easiest, or the thing that people tend to think of as the first thing in trigonometry. Solving right triangles. And the reason that I want to go through this is because in the past, you have probably dealt with right triangles using almost exclusively the sine and cosine functions, occasionally tangent when you can't avoid it, and avoiding the other trigonometric functions at all costs. Because we are going to be relying on tangent and secant so much, we need to make sure that we're comfortable using those functions as well. So consider this right triangle where I have an angle theta marked. I've got a couple of sides marked down. I'm calling them A and B. So let's call them A and X. Well, my default when I look at this is to think cosine, but again, I want to start thinking in terms of secant. Well, if cosine is adjacent over hypotenuse, and secant is the reciprocal, then secant would be hypotenuse over adjacent. So in this case, the secant of theta is x over a. Then, to get the third side of the triangle, I guess I could call it b. A squared plus b squared is equal to x squared, which means that b squared is x squared minus a squared, and b itself is the square root of x squared minus a squared. Yes, technically there should be a plus or minus, but you know by this point that it's a triangle, so it has to be positive. We don't have to worry about it. All right, so now that the hard one is out of the way, let's take a look at a triangle where we have these two sides. This is the opposite and adjacent legs. The relationship between those two legs is the tangent, so tangent of theta is equal to x over a. And the third side, I guess we can call it c. That's the hypotenuse, so x squared plus a squared is equal to c squared. Just flipping the equation around and then taking the square root gives us something that looks more like that. And saving the easiest for last, in this configuration, we have the opposite leg, we have the hypotenuse. Sine of theta is equal to x over a. And the remaining leg, if we call that b, well, we're going to have x squared plus b squared is equal to a squared. And b is equal to the square root of a squared minus x squared. All right, so that's a bit of a strange way of thinking about things, solving these triangles in a very abstract sense. But I want you to get a little bit of practice thinking about it, or a little bit of a head start thinking about that, because all of these ideas are going to be coming up again. Now that I've gone through all of the abstract things, though, let's wrap up with something relatively straightforward and put some numbers on one of these triangles for you to solve. All right, so your task is to solve this right triangle and to give everything in terms of exact values. Exact values can sometimes look very strange, but I think at this point you understand what we mean. So take a couple of minutes, see what you can do with that, and I'll see you in the next video.